Australia's future is underpinned by its minerals, energy and groundwater resources. These resources are needed now more than ever as Australia and our global partners strengthen our low emissions economy. Committed to securing Australia's future as a global supplier of the resources necessary to support the net zero transition, the Australian Government has established Resourcing Australia's Prosperity, a $3.4 billion initiative being led by Geoscience Australia. Over the next 35 years, Resourcing Australia's Prosperity will play a key role in unlocking new opportunities to supply the materials required to support our economy, grow our resources sector and maintain our national security. This new information will underpin targeted exploration to help lower investment risk, support government policy decisions and provide communities with the tools to inform natural resource management. We'll work closely with our stakeholders to help them realise the benefits of pre-competitive geoscience data and information and continue to build strong, lasting relationships with First Nations peoples to create further collaborative opportunities. By partnering with Commonwealth, state and territory governments, our research partners and communities, this landmark initiative will ensure a sustainable, thriving and resilient Australia for future generations.
Well, good afternoon everyone and welcome to the first webinar for the 2026 for the Resourcing Australia's Prosperity Initiative. My name is Dr. Andrew Heap and I'm Chief of the Geoscience Australia's Minerals, Energy and Groundwater Division and I have the pleasure of emceeing today's event. Making hydrogen storage work at scale is the first in a series of webinars we propose to hold this year and is just one of the many mechanisms we are implementing through the Resourcing Australia's Prosperity Initiative to inform, share and discuss with our stakeholders the pre-competitive geoscience work we are undertaking this year. In today's seminar, we will discuss Australia's potential for geological storage solutions, with a focus on hydrogen, a topical issue given the recent focus on energy security. I would like to begin by acknowledging the traditional owners of the land on which we meet today. Geoscience Australia values the lands, water and sky as we work to deepen a shared understanding of country and earth. We respect First Nations peoples and their enduring connection, contribution and obligations to country. Reflecting on our shared history, we are committed to listen and learn. The Resourcing Australia's Prosperity Initiative is a multi-decadal investment by the Australian Government in pre-competitive geoscience. It provides a platform for Geoscience Australia to influence and support Australia's long-term prosperity and a future made in Australia by strengthening our knowledge and understanding of Australia's minerals, energy and groundwater resources. The goal is to provide additional confidence to decision makers on future investment decisions regarding the responsible development and ongoing stewardship of Australia's resources. Unlocking Australia's resource potential is a key national focus area of Geoscience Australia's new 10-year enterprise strategy, Shaping Our Future. Shaping Our Future provides a clear direction on how we will continue to provide trusted pre-competitive geoscience data, information and insights, which is underpinned through delivery of this exciting initiative. Resourcing Australia's Prosperity helps address Australia's national challenges and opportunities across our economy and globally. This includes the net zero transition, building sovereign capability across the resource value chain, and delivering new data and insights on Australia's resource potential at a national, regional and commodity level to stakeholders through innovative technologies and digital solutions. In addition, consistent with Geoscience Australia's commitment to strengthen partnerships and build strong and lasting relationships with First Nations peoples, we will undertake respectful and meaningful engagement with First Nations peoples through partnerships and co-design work programs and knowledge sharing. Hydrogen is a key component of the Australian Government's net zero transition, providing a potential energy solution for decarbonising hard-to-abate industries, supporting cleaner fuels and feedstocks, and when paired with renewables, helping manage energy variability through long-duration energy storage. Australia's updated 2024 National Hydrogen Strategy sets out the Australian Government's objectives on developing a hydrogen industry, focused on scaling clean hydrogen, building demand in priority sectors, and working with industry and states and territories to grow domestic capability and export opportunities. But to make hydrogen work at scale, we also need the enabling infrastructure, especially storage. Storage is what turns production into reliable supply, supports seasonal balancing, and provides resilience for industry and the power system. That's why today's topic, making hydrogen storage work at scale, matters. In many settings, economical underground hydrogen storage is likely to be essential because it can offer the volumes needed for weeks to months of supply at costs that are difficult to achieve above ground. We have a great audience today, spanning government, industry, research and the geoscience community, including international colleagues, so welcome to you all. We have 90 minutes and there's a lot to discuss, so let's get started. Our first speaker today is Terry McHugh from Courault, a design, engineering and advisory company. Terry is a chemical engineer and senior consultant in the hydrogen and industrial decarbonisation team at Courault. He has delivered a range of hydrogen projects spanning strategic advice through to concept and feasibility studies for both industrial and government clients. He is passionate about supporting clients navigate the complexity of decarbonisation, helping them to understand the role that hydrogen and its derivatives can play while ensuring the long-term success of heavy industry in Australia. Terry will discuss infrastructure assessment for the hydrogen industry today. Welcome, Terry.
All right, we'll kick off. So good afternoon, everyone, and a big thanks to Geoscience Australia for having me this afternoon. So as mentioned, I'm going to be walking through some of the work that we've recently wrapped up with the Department of Climate Change, Energy, the Environment and Water, which is a bit of a mouthful. So from here on, I'll refer to simply as DQ. This work has been completed over the past 12 months. All right, now I'm going to jump into a bit of the context behind this project. So as Andrew covered, Australia is aiming to be a leader in the global hydrogen economy. And guiding this vision is the National Hydrogen Strategy, published by DQ, the latest version in 2024. This document outlines the key actions needed to get there. One of the actions outlined in this strategy is a review of the National Hydrogen Infrastructure Assessment, the NHIA. This document was last published in 2023 and was based on research conducted within 2021 and 22. Since then, our understanding of hydrogen's role in achieving our decarbonisation goals has matured significantly, and the industry has faced a number of challenges. And unfortunately, we have seen a number of high-profile project cancellations, primarily due to the high costs associated with hydrogen production. Some of the findings that we'll go into today will discuss these challenges in a bit more detail. In response, the Australian government is actively implementing solutions to overcome these challenges, including initiatives such as the Hydrogen Head Start program and the Hydrogen Production Tax Incentive, both providing financial incentives. In preparation for the next revision of the NHIA, due later this year, Courault were engaged to complete this infrastructure deep dive study. The focus of this study was to identify the priority infrastructure focus areas for further investigation and resolution as part of the next NHIA. For those of you unfamiliar with Courault, we're a large engineering, design and advisory consultancy headquartered in Australia. We've been extensively involved with some of Australia's most prominent hydrogen developers, and our experience has spanned the full project lifecycle from concept and feasibility studies through to detailed design and execution planning. Now I'm going to take you through a bit of an approach, the approach we took to this study and an overview of our key findings. So I'd like to draw your attention to the diagram on the left. So first thing we did was we broke down the entire hydrogen supply chain into individual components shown across the top row in black. So running from left to right, we have water supply, power generation, power distribution, hydrogen production, hydrogen distribution, storage, conversion to derivatives, and ports and marine. For each of these components, we undertook 3 activities. The first was a current state assessment, providing DQ with an updated picture of current sentiment and challenges observed within the industry, capturing findings from our work with hydrogen proponents and also from public reports and studies. The next activity we did was producing an up-to-date cost database of the core hydrogen supply chain components. So to do this, we leveraged some previous cost estimates that we'd produced for Australian projects and complemented this data set with publicly available information. For certain components, those highlighted in blue, we then went to a deeper level of study to assess the potential for repurposing some existing infrastructure and to investigate scenario trade-offs. Additionally, we built a techno-economic model which assessed the cost implications of different hydrogen transmission methods, namely looking at pipelines versus tube trailer transportation or trucks. Today, I'm going to focus on the core findings and recommendations made for the department and then finish up with a bit of a comparison on above ground and underground storage that we did earlier on in the study, which will then lead to our next presenter. The 3 key findings from the work are shown on the right. The first is around some of the major challenges facing industry at the moment, specifically relating to cost-effective power supply, port infrastructure, hydrogen transmission, and lengthy project timelines. We also suggest that the strategic planning is required to ensure that the most cost-effective method of hydrogen transmission can be achieved. And then when comparing underground and above ground storage, there is significant cost savings that may be able to be realised through the use of underground hydrogen storage. However, there are some hurdles to overcome. All right, so getting into some of the infrastructure challenges. The most prominent one and up first is power supply. Securing sufficient cost-competitive renewable energy remains a primary barrier to wide-scale hydrogen adoption. Renewable hydrogen is an extremely energy-intensive process, making up about 60% of the total cost of production. Efforts to reduce the cost of supplied power are the most effective option for increasing the viability of projects in Australia. On the second point, Australian ports will require targeted upgrades and new infrastructure support to support hydrogen exports, including storage, processing, and loading facilities. While some ports already handle commodities like ammonia, additional capability will be needed at scale. Some of the challenges include constrained land availability, especially considering the footprint required for portside production. Furthermore, owing to the hazardous nature of hydrogen and derivatives, there is a need for very large separation distances between those sites and neighbours, limiting the number of suitable locations. Separately, ports will need upgrades to accommodate the import of large renewable energy components, such as wind turbines. On hydrogen transport, so whilst pipelines typically offer the lowest cost transmission method for large-scale hydrogen transport, there are currently no operational large-scale hydrogen pipelines in Australia, and the regulatory landscape is still evolving. This study also investigated repurposing of existing natural gas pipelines, and whilst this can potentially reduce approvals timelines and costs, there are technical challenges to overcome, such as material compatibility issues and reduced operating pressures. On project timelines, so proponents have faced extended lead times for some key processing equipment required for hydrogen production. This includes things like electrolyzers and compressors. However, there are positive signs that this is now improving. Furthermore, approvals timelines are extensive. Owing to the first-of-a-kind nature of hydrogen development, the hazardous nature of hydrogen and its derivatives, and the scale of the proposed projects. I'm going to walk you through some of the results of the modelling we did on hydrogen transport. So I'd like you to consider the scenario whereby we have a hydrogen production facility that's co-located with a renewable energy generation site, so say an inland facility. Then we have an end user located some distance away. And we want to know what the lowest cost solution is for transporting that hydrogen. The diagram on the left summarises the findings of our modelling. Along the x-axis, we have the distance from the production site to end user in kilometres, spanning 0 to 2,000 kilometres. And on the y-axis, we have the hydrogen throughput to the end user. in tonnes of hydrogen per day. The area shown in yellow above the dotted line represents all the combinations of throughput and distance where it is cheaper to use a pipeline. Conversely, the area in blue where it makes sense to use a tube trailer truck. The key point I'd like to highlight is that above the break-even horizon noted, at about 40 tonnes a day of hydrogen production, or about 100 megawatts of electrolysis, pipeline is cheaper across all distances. Importantly, the exact position of that break-even horizon depends on the modelling assumptions and inputs. However, it remains that pipeline is often the preferred solution for large-scale transmission. There are some additional considerations and trade-offs that need to be considered by project developers. On operational flexibility, pipeline networks are geographically fixed and difficult to reroute once constructed, while in contrast, truck-based transport offers significantly greater operational flexibility, with the ability to adjust routes and number of trucks in response to changing demand. Mountainous terrain or large bodies of water will make pipeline construction challenging, potentially improving the business case for truck transport. And importantly, on carbon intensity, the use of diesel-powered trucks will increase the carbon intensity of your delivered hydrogen. Conversely, a pipeline offers a much lower carbon intensity option. We do have the option of using fuel cell-powered trucks for transport of hydrogen as well. Okay, so now onto some of the recommended actions. First is on government-led investment in common user infrastructure, such as low-cost renewables, transmission development, port readiness, and water supply infrastructure could improve commercial viability of projects and improve investor confidence. We've also highlighted the need for a coordinated approach between federal, state, and territory governments as critical for developing a clear, robust pathway to hydrogen scale-up. On the second point, whilst policy was not the focus of this study, this work has highlighted that many hydrogen supply chain technologies, such as hydrogen pipelines, tube trailers for transport, hydrogen storage solutions, which have been successfully deployed globally elsewhere, are yet to be commercially deployed in Australia. The proactive development of policy, safety guidelines, and permitting standards is essential to avoid project delays and provide confidence that infrastructure will be supported by fit-for-purpose regulation. And thirdly, the preservation of key transmission and pipeline corridors into prospective hydrogen hub and strategic port locations, for example, Gladstone in Queensland, the Hunter region, New South Wales, Port Bonython in South Australia, Kwinana in WA, or Bell Bay in Tasmania, will protect long-term infrastructure opportunities and reduce future development costs. Onto our analysis of above-ground storage. So our analysis focused on type 1 steel vessels, known as bullets in industry. There's an image there on the left. So bullets are the most common observed amongst large-scale hydrogen project developments and generally represent the most cost-effective solution, unless, of course, geological storage options are available, which we're going to be diving into today. Other options for above-ground storage include spherical tanks for storing very high pressure or liquid hydrogen, smaller composite cylinders, or metal hydride storage. Bullets are typically operated at pressures of around 60 to 100 bar, and each vessel is capable of storing about 1.5 to 2 tonnes. In terms of size, these things are massive, about 24 metres tall and 3 metres in diameter, although they can be scaled up and down. Owing to the small size of the hydrogen molecule, the bullets are required to have very thick steel walls in order to prevent leakage, around 5 centimetres wall thickness for the vessels shown on the left. This creates a couple of challenges. First is that production costs are very high due to the sheer quantity of steel required. Second is that the vessels are extremely heavy, around 70 to 80 tonnes empty. The size and weight of these presents logistical challenges for transporting these vessels to site, may necessitate on-site fabrication in some instances. In terms of cost, our experience shows that these typically cost around $3.5 million per tonne of stored hydrogen for large-scale projects. On above-ground storage, I quickly wanted to touch on the effect of pipelines and their impact on storage. So pipelines are dual purpose. They enable transmission of hydrogen, but also function as storage. This is known as line pack storage. For longer pipeline runs, this can have a material impact on the required storage requirements. As an example, we modelled a 100 kilometre, 10-inch pipeline, or DIN 300. The usable storage quantity was about 13 to 14 tonnes. At $3.5 million a tonne, you can imagine that this can result in some significant reductions in costs and on-site storage requirements. Taking a closer look at underground storage. So underground storage refers to the use of salt caverns, depleted gas reservoirs, aquifers, or lined rock caverns. My fellow speakers will be exploring these in greater detail. The map on the left-hand side was produced by our friends at Geoscience Australia and illustrates some of the work that they've done in mapping out potential salt cavern locations across Australia. One of the challenges is that you are constrained to areas which can support this type of storage. And if, for example, you are seeking to build a hydrogen production facility near a New South Wales renewable energy zone and export ammonia through the Port of Newcastle, underground storage may not be a feasible option. However, as shown in the map, there are locations around Australia that might be suitable. Whilst there are only a handful of operating examples globally, studies suggest that the cost of underground hydrogen storage may be as low as an entire order of magnitude or cheaper. That is 1/10 the cost compared to above ground storage solutions. Hence, there is a lot of discussion and focus on this as an opportunity to help bring down the cost of hydrogen. That's about all we got time for today. Thanks very much.
Thanks, Terry, for that wonderful presentation. And as Terry alluded to, there will be time after our speakers today to ask questions. So get your questions ready. You can ask questions of all of our speakers. We have about 30 minutes at the end. You can ask questions of all of our speakers using the Q&A function in Teams. So now we have Dr. Andrew Feitz, who is the Director for Energy Initiatives and Advice at Geoscience Australia. Andrew leads the hydrogen assessments team as part of Resourcing Australia's Prosperity. He holds a PhD from the University of New South Wales and has worked as a senior researcher in air and water treatment technologies at the University of New South Wales and the Karlsruhe Institute of Technology. Andrew is an environmental engineer and has over 10 years research experience in the geological storage of CO2. Andrew's research interests include salt exploration for underground hydrogen storage, green iron, and Australia's natural hydrogen potential. And today he will give us an update on the National Hydrogen Hub Storage Assessment now underway. Welcome, Andrew.
All right. Okay, well, yes, thanks very much, Andrew, for the introduction. And many thanks to Terry for setting the scene for my talk. As we've learned from Terry, there is a real potential for underground hydrogen storage to potentially reduce the costs of hydrogen storage in comparison to above ground tanks. So over the next 15 minutes, I'll discuss underground storage options for Australia. This is going to be an update. We haven't completed our assessment yet, but I'll share what we've found to date and some of our future plans. But first, let's have a quick look at the hydrogen landscape in Australia as it stands today. Here's a map of all the hydrogen projects we know about in Australia, compiled by our sister science organisation, CSIRO, through their great High Resource website. All the currently operating projects shown in green are small pilot scale facilities, but there are many other projects in white that are in planning, and some of these are very large projects. Currently under construction, these are the projects that are highlighted in orange, and they are also pilot to demonstration scale projects. The map also includes the location of the hydrogen hubs in yellow. It's fair to say that establishing a hydrogen project in Australia, well, for that matter, anywhere in the world at the moment, is hard. It's expensive, and particularly for green or renewable hydrogen, the tech is still evolving, and it's had its problems when scaling up. Glitchy is a word I've heard used. There have also been some high-profile, large-scale projects that have been cancelled too, as Terry had mentioned previously. So, and the other complication is costs have been rising, not falling. But over the longer term, hydrogen technology advances and the mass production of technology like electrolyzers should drive down these costs. But today, we're starting from a small base and it's hard. All of these projects, if they are successful, will need hydrogen storage of one kind or another. For some projects, that might be tens of kilograms or maybe a couple of tons, and that'll be in above ground high pressure tanks or short pipelines. For other projects, they may require thousands of tons of hydrogen storage to ensure a steady supply of hydrogen to a low emission industrial hub or for plants making products like green iron or ammonia. Having literally thousands of above ground tanks, as you saw from Terry's slide, is just not simply practical for a project or cost effective. And this is where underground hydrogen storage becomes important. Geoscience Australia has committed to produce a national hydrogen hub storage assessment in 2027. It will assess the most feasible underground storage options for each of the planned hydrogen hubs, included depleted fields, salt caverns, and mined rock caverns. Depleted fields occur when natural gas has been extracted from rocks underground. Sometimes the gas is re-injected into these fields to create a seasonal gas storage buffer, like we see at Lockhart Energy's Iona plant in Victoria. Now, Lockhart Energy has recently completed an ARENA project with the help of Courault to assess the technical feasibility of hydrogen storage in a depleted gas field. This study shows that depleted gas fields look really promising for hydrogen storage, but it's still at an early stage, with pilot scale testing happening around the world. There are also particular geological requirements required for it to be successful. But we look forward to seeing future demonstration trials of hydrogen storage in depleted fields and confirmation that this is a really cost-effective solution at scale. Another option is to store hydrogen in salt caverns. The salt required for a cavern is the same rock salt you use in your salt grinder at home, sodium chloride or halite. This type of storage is used for storing commercial quantities of hydrogen around the world today, with many more planned and under construction. These caverns are typically located sort of 500 to 1500 meters underground. Essentially, you can mine out a cavern if it is shallow enough, like in this photo, or drill a well into a thick underground accumulation of rock salt, pump down water, and dissolve out a huge underground tanks. These solution mine underground tanks are approximately 60 meters in diameter, if you can picture that, and can be hundreds of meters tall. Capucine will be giving more details on this type of storage in the following talk. The other option that we're looking at is mined rock caverns. Mined rock caverns are used around the world for storing products like crude oil, LPG, and ammonia. There's a small pilot being used for hydrogen storage in Sweden. We are looking in more detail what are the geological requirements and costs for constructing mine rock caverns in Australia. This map shows the location of depleted gas fields around Australia and our best knowledge to date of where thick underground salt resources are located. So let's have a look at the depleted gas fields first. These are the bluey-green diamonds on the map. And for this study, we're only considering onshore gas fields. So as you can see from the map, onshore depleted gas fields are mostly located far from the hubs. Exceptions are around Perth and the Midwest region of WA. You can see a few over there, which look to be well located. Gas fields located at the very bottom of Victoria, and you probably can't quite see that, but it's at the very bottom, not far from the iconic 12 Apostles. They could potentially store hydrogen projects in that region. But it's worth noting that not all depleted gas fields will be suitable for hydrogen storage. It's likely to be few that will be. It depends on the permeability of the sandstone rock, the groundwater pressure, the size of the field, and the depth. If the permeability is too low, you'll struggle to get the hydrogen out again once you store it underground, making storage indeed very expensive. The other complication with gas fields is they already contain methane, so this will be mixed with hydrogen as you put it in, although that will change over time. That might be okay if you're using hydrogen to power a turbine for electricity production, but it's not so good if you're looking at using hydrogen as a feedstock into a manufacturing process. That would require a further cleanup and separation step. Okay, now let's turn our view to having a look at the salt. So the solid light green blobs you can see on the map show where we've mapped salt that is relatively pure, thick, and might be suitable for a salt cavern construction. The green hashed areas in Western Australia show areas where there is a lot of salt, but it's in thin layers mixed with other types of rocks, what geologists call interbedded, and it's probably not suitable for cavern construction. There is the possibility that there could be salt structures within those hash areas that might be suitable, but so we haven't fully discounted it. It's just that we haven't found any evidence of this at the moment. The purple blobs are what we call salt leads, where we can see something that looks like salt deep underground from seismic surveys, but we don't have physical proof that the salt is the right kind of salt. There are likely to be many more of these leads, particularly in Western Australia and South Australia region, but they haven't been discovered yet. As you can see though, on a whole of picture, the salt accumulations are mostly located far from the hubs as well. So in Eastern Australia, we have the Boree salt. That's the only one we know of that occurs in Eastern Australia. There's thick salt in the middle of Australia, what we call the Chandler Formation, but it's also a long way from hubs. There are from old wells that were drilled in the offshore polar basin to the west of the Eyre Peninsula of South Australia. We can see thick salt in the Courault Formation, approximately 1 kilometre thick. There's really a lot of salt there, but it's only been found offshore. There is a chance, though, that salt extends closer to onshore, possibly even closer to shore, possibly even onshore. An area of interest to us, though, is up near Darwin. You can just make out some tiny small spots up there off the coast, where I've highlighted it in that red circle. These are reported salt diapirs, and there is a chance that these could be located closer to the shore, maybe even onshore. So this is a really exciting area for us to have a look at. That area connects well with existing pipeline easements as well. So this is pretty interesting. Now, I haven't shown the location of prospective sites for the mined rock caverns on this map. And the reason for that is that they can all be potentially located within approximately 50 kilometers of each of the hubs. So basically where all the current yellow hub markers are at this national scale. And this is the big advantage of mined rock caverns. And we'll explore this a little bit more over the next couple of slides. Geoscience Australia has recently published work on hard rock caverns and lined rock caverns and the application to Australia. We commissioned 2 studies. There's a study by Geoscience, which we'll hear a little bit more about in the next talk, to conduct a study on whether hydrogen could be stored in lined rock caverns and look at some particular sites around Australia. A second study was commissioned to Lane Power and Energy Solution in the US on unlined rock caverns and whether they could be suitable for hydrogen storage. So these 2 reports are available online if you want to have a look at them. They outline the economics of hydrogen storage. They talk about that building underground caverns has high upfront costs, much like above ground storage tanks in terms of high, but certainly not as high as $3 million per tonne. But the running costs are lower because the caverns are naturally protected underground. And the reports discuss key operational considerations like how much rock, how the rock must behave to safely contain gas, risks such as hydrogen embrittlement or too much pressure, along with ways to manage them. So let's have a look at some of these findings. So mined rock caverns are essentially artificially created mined out caverns that are typically found in hard rock formations like granites. that can be used for storing various materials. So mine caverns can be unlined, and this is the case for most of them around the world, or lined. Mined rock caverns have been used globally for decades as reliable subsurface storage. They're usually used for hydrocarbons with low vapor pressure like propane or LPG. The length of these caverns is typically about sort of half a kilometre to a kilometre long, and depths about 100 to 150 metres underground. They need a good water pressure head to maintain a good seal. Now, the beauty of these caverns is they enhance energy security by providing stable, high-capacity storage, largely unaffected by surface conditions. The first mined cavern was constructed in the US in the 1950s, and since then there's over 400 caverns around the world. And we have one in Australia too. The Elgas LPG project in Port Botany in Sydney is a notable example of a mined rock cavern for LPG storage, and that's been operational for over 2 decades. One issue with unlined caverns is they operate at relatively low pressures, around 10 bar, which is not efficient for hydrogen gas storage, making this type of storage expensive. So we need to increase the pressure that the hydrogen can be stored underground. This can be achieved by lining a cavern, and Geostock will talk about this more in the next talk. Another interesting fact is I wasn't aware of this until fairly recently, but mined rock caverns have also been used for refrigerated ammonia storage. So refrigerated ammonia is at minus 33 degrees. There's examples of these in Norway and in the US. So what essentially happens, you pour the liquid ammonia into a cavern, and it essentially freezes the rock and the water within the rock. So you create like a sort of big ice ball within the rock, and there's a cavity inside which you can use to pull out the refrigerated ammonia. And it turns out that this could be actually a cost-effective way to store ammonia underground in comparison to above ground tanks. Okay, but as we get to the conclusion of this talk, what about the cost? And this is what it's all about. Well, here are some capital costs of different options published in recent reports. 300 million for a salt cavern is definitely on the upper end, I would say. I've seen estimates closer to 100 million. Mined rock caverns have much higher capital costs compared to a salt cavern, however, and we're talking in the order of about $900 million for 1,000 tonnes. We suspect that the capital costs for depleted field storage are cheaper than for salt storage based on what we know about drilling costs, but we don't have published numbers in Australia yet. However, based on the numbers that you see on the slide, you would think, well, let's go with a depleted gas field. It seems to be the cheapest option, right? Well, it's not that simple, because what we really want to know is how much hydrogen could be delivered each year. So think of the petrol tank in your car. Well, actually, maybe not, because unless you want to cry, but filling it up once a year is not going to get you very far. It's the number of refills each year which is important. And when we include the number of refills into the equation, you can see that a depleted gas field can do 1 or 2 cycles per year, a salt cavern roughly 8 cycles per year, and a lined rock cavern potentially weekly. And once you take into account the cycling and the operational costs, we can derive what's called a levelized cost of storage. So in that respect, salt caverns are certainly cheaper than mined rock caverns, but we also suspect they're probably cheaper than depleted fields based on what we know about drilling costs and the reduced number of cycles that you get with a depleted field. Once we get published updated numbers on this, that'll really help us work out what's the cheapest option. But perhaps lined rock caverns aren't too different to a depleted field if they can maintain a high cycling rate. The beauty of salt caverns is that with the vertically solution mined ones, they're just separated by a few hundred meters, which means you can have multiple caverns in the one area, and this helps to reduce the costs further. And this is why GA is focusing on finding new salt accumulations. Over the next few years, we plan to fly airborne surveys over different parts of the country and using geophysical techniques like gravity gradiometry to look for signatures of salt deep under the earth. We will once we sort out where the potentially suitable depleted fields are located, remembering that not all depleted fields will be suitable. Let's filter down to those that could be, map out the salt as best we can. Then we can start to join the dots and work out what's the best underground storage options for each of the hubs, balancing long pipelines with potentially cheaper storage options further away versus shorter pipelines, but more expensive storage. So the solution is going to be different for each of the hubs. So stay tuned for next year when we release our report. And with that, I'll finish up and I look forward to your questions during the Q&A. Thank you.
Thanks, Andrew, for that wonderful presentation. Yeah, subsurface ice balls. I suddenly had a flashback to Indiana Jones, but hopefully we don't see that in the risk assessments. But just a reminder for people that you can provide Q&A to all the speakers at the end of the next presentation. So please get them ready. And look, we're very fortunate to have two international industry speakers joining us today. At times that are not really convenient for them, so we really appreciate that they have taken their time to be with us today. First, we have Elodie Zausa from Geoscience in Paris and Capucine Courault from Geoscience Canada, dialing in from Houston. Elodie is a Sales and Business Development Director at Geoscience, an international company specialising in designing, supervising construction and operating underground storages for all types of energy. Elodie promotes the development of underground storage solutions for new energies. And with 20 years experience in the oil and gas industry, and more recently in new energies such as hydrogen and ammonia, as well as CCUS solutions, Elodie has broad knowledge of the energy sector from production to end users. She earned an engineering degree from École Centrale de Marseille in France and a PhD in chemistry from the Institute of Research on Catalysts in Lyon, France. Capucine is a geologist with 18 years of experience in underground storage projects in salt caverns, porous media and hard rock mine caverns for hydrogen, and more recently for hydrogen and helium. Over the past 5 years, she has also been providing geology support and peer review for UIC permitting for Class 6 carbon dioxide storage and Class 1 waste injection wells. She earned a master's degree from the geological engineering from École Nationale Supérieure de Géologie in Nantes, France, and Capucine is a licensed professional geologist in Texas, Louisiana, and Illinois, and a member of the Solution Mining Research Institute. Please welcome both. Elodie and Capucine will provide an overview of underground storage of hydrogen with a particular focus on mine-lined rock caverns, as we've heard. Please welcome both Elodie and Capucine.
So thank you for inviting us. Thank you to Geoscience Australia for the invite. I'll start first with the first part of the presentation. Geoscience, for the one who doesn't know us, is an international company with a headquarters based in France. We are specialized in underground storage, all the techniques, so we covered a lot. You heard about mine cavern, salt cavern, and porous media. And what you can see, we have a worldwide footprint. We have done projects in many countries, more than 50 worldwide, with some subsidiary. Capucine is based in the US, Geoscience Australia, and here is the scope of what we cover. We cover actually all the phases to develop underground storage, from the geological screening to the commissioning and the operation and maintenance of the cavern. So it means all the phases, means the development of the pre-feasibility, feasibility studies, supervision of the construction, and then commissioning and operation of the caverns. And these for all type of energy. We will focus on hydrogen, but we've been created 60 years ago for the development of French strategic stock in France for oil and gas. So here you have few pictures about underground storages. The one on the left, starting with the one on the left, it is mine cavern in France to store LPG. In the middle is porous media to store natural gas in Spain. Then you have mine cavern again to store crude oil in Singapore. And on the right-hand side is salt cavern. They store crude oil, refined product, natural gas, and there's one of the biggest projects in France for storing hydrogen, 6,000 cubic meters. Tons, sorry, 6,000 tons of hydrogen. So here you have a picture of all the techniques, the existing technique to store energy underground. And we have highlighted in green the, let's say, the decarbonized energy that could be stored underground. So as you can see, hydrogen in salt cavern, hydrogen in porous media, Andrew talked about it. We store as well. We could store, hydrogen in unlined cavern. We do not mention that because pressure, maximum pressure is very low, is about 10 bar if the cavern is at 100 meters deep. So that's why we don't mention that technique for hydrogen. And the new one we developed is the line mine rock cavern. And well, here is the list of all the advantages regarding underground storage from an economical point of view. Safety, we see that quite a lot, unfortunately, right now in the Middle East, and environmental protection as well. So if just to give you a quick look about we speak a lot about hydrogen, and we also see that in our activities since 2020. We have done quite a lot of studies worldwide regarding development of hydrogen project, mainly in Europe, as you can see, and we distinguish the three techniques. In orange, you have the porous media studies, blue one for the salt cavern, and the pink is for the mine line rock cavern. We have quite let's say, well advanced project in Europe regarding line mine rock cavern in the UK and Ireland. And regarding porous media, so I will focus on that. So here you have the advantages, a summary of the advantages and pro and cons, let's say, about all those techniques. So clearly the salt cavern is the most proven one. There's no stopper or already existing caverns in the US and in the UK. Of course, as Andrew said, for that technology, it requires a specific geology that is not available everywhere. We'll see that later. And also, we need quite a lot of water for the process of creating the cavern, the leaching process. And if you are inland, not too close from a source of water, this could be a difficulty as well. If we move on the porous media, there's a very good studies that has been done with Geoscience as a leader during 2 years, regrouping academics and industries. It's high stories. You could find all the detail online, and that study is cover quite a lot of the question you may have from a technical and economical point of view. This technique, we clearly see that one for very large volume of hydrogen, and is not as reactive, let's say, on a day-to-day basis. We recommend to go for the salt cavern instead. And the last one, and I'll give you the floor, Capucine, is about the line mine rock cavern. As we said, salt is not everywhere, so definitely you go for salt cavern if you have salt. But if not, we recommend the line mine rock cavern if we think about storing massive quantity of hydrogen, and we developed that technology just because salt is not everywhere. Capucine, the floor is yours.
Yeah, thanks, Elodie, for this overview. And now I'm going to dive into the mine line rock caverns. And a lot of the slides presented here are part of the studies that Geoscience performed for Geoscience Australia. And so you can find them in these studies that is publicly available. A brief history. So for mine-line rock cavern, the concept started to be looked at in the 1980s for natural gas, and then more recently, like for hydrogen in Sweden. You can see that most of these pilot projects were in Sweden and in Japan, and the reason is that the geology of these two countries, like the rock underground, is mostly hard rock. So for these countries, that's the only option. So if you go to the next slide. So why mine-line rock cavern? And this has already been introduced by Andrew and by Elodie. It's really the concept of if unlined mine cavern, if you're looking at hydrogen, you are limited to less than 10 bar. And if you use like a liner, you can go up to 250 bar. So basically the constraint of being less than 10 bar is that the quantity of hydrogen stored will be very small, so most likely uneconomical. However, as Elodie presented in a slide before, you can consider ammonia storage in an unlined mine cavern. And if you go to the next one, so this is a high level of like the design workflow for such caverns. So you look at the operating needs, injection, withdrawal flow rate. You look at the rock mass parameters, the capacity needs, and then with a lot of like rock mechanic analysis, you establish like the diameter of your cavern. And these caverns having a shape like more of a vertical shape and curved at the top and at the bottom, they're often called silos because they look like silos. And so you estimate diameter, depth, height, the thickness of your steel, a lot of parameters that will allow like to build your cavern. And if you go to the next slide, so this is an example of some parameters that are looked at. For example, if you assume a certain cavern capacity, a minimum pressure, maximum pressure, so you calculate a geometric volume for your cavern, and then you have a concept which is a concept of uplift. So when you're at maximum pressure, like the pressure from your hydrogen would push the liner, and so would break the liner if you don't have enough weight from the rock above. So you look at a certain cone of influence of like the rock above the cavern, and you calculate like what is the depth, like the minimum depth that you need to place your cavern at to still go through a safety factor of 2. And if you go to the next slide, so this is some aspect of construction, and just focusing on the slide on the left. So we speak about a line rock cavern, but as you can see, there is one steel liner, but that's not just a steel liner and then just the rock next to it. You have like from item 2, the sliding layer, to item 6, the drain pipe. You have all these elements, and they're really like a buffer, almost like a sponge, maybe like a mat when you do gymnastics, something that would help break the pressures that when you're at maximum pressure from the cavern, or when you have when you're at minimum pressure from the cavern, you get the pressure from the rock mass and from the water underground. So all this layer, like the steel liner, but the layer like 2 to 6 have to be designed properly to really accommodate like this swing of pressure, so that the steel liner doesn't break during the operation. And if you go to the next slide, so these are some aspects for the typical surface facilities equipment for such hydrogen underground storage. So the main equipment are like filtration, metering, compression, like a three-stage compression, and then like piping, vent, peak traps, and things that are, if some of you are familiar with underground storage for hydrocarbons or natural gas, it's quite similar with what is already existing for underground storage. And if you go to the next slide, so this slide and the next slide presents some aspect about cost. And so we break the cost into subsurface cost and surface cost. So subsurface cost, it's between 300 Australian dollar per kilo to 2,000 Australian dollar per kilo. And really the driver for subsurface cost are the capacity and the geology. So large capacity, favorable geology will drive like some lower subsurface cost per kilo. And then the surface cost, oh, sorry, if you go back to the, surface cost, you look at, you're looking at 100 million to 1100 million Australian dollar. So here, like it will low delivery rate, lower surface cost, and higher delivery rate and higher surface cost. And then if you go to the next slide, this shows like the total cost, and it's taking the example of a cavern of 1,000 tons, which is a reasonable size, like for such a storage project. So the three on the left shows the example with a good work, a very good work, and an excellent work, and you are looking at a variation of like approximately 800 to 1,000 Australian dollar per kilo. What you can notice with the one in red on the right is that if you're looking at the same excellent work, but at a higher tonnage, you are decreasing your cost to 600 like Australian dollar per kilo, looking at like just with a higher quantity. And another aspect is OPEX per year, which are estimated to be like 2 to 4% of the capex. And another thing which is not presented here but is in the study is if you plan for many cycles of injection withdrawal per year, this will lower over the history of your storage. This will lower your unit rate of cost per kilo. And if you go to the next one, so these are the 11 sites which were selected by Geoscience Australia. They are related to the hub that were presented before. And so what Geostock did and what is presented in this study is a preliminary design for each of these locations when hard work was like present at the site. And so the design consisted of looking at an envelope of like depth of this cavern, how many silos were necessary to accommodate the quantity of storage provided by Geoscience Australia, and the height, diameter, and pressure of these caverns. And that's all for the dive-in, and thanks a lot for your attention, and please do not hesitate to ask questions during the Q&A.
Thanks, Capucine and Elodie, for that very detailed presentation on some of the practicalities of hydrogen storage. It's great to see that analysis being done. So now this is the time for you as the audience to take an active participation role in our webinar today, and we have time to take questions for today's speakers. We have about 30 minutes, so please send in your questions. And as I said, to ask a question, please use the Q&A function in Teams at the top of your screen and not the chat function. A chat function won't work for this event. If we run out of time or if a question requires a lengthy or detailed answer, we may take it on notice. So please include your name with your question and we will contact you following today's event. So for Terry, first question, can hydrogen storage play an important role alongside the expansion of renewable energy, particularly due to the nature of renewable energy sources?
Yeah, thanks, Andrew. Yep, so short answer is absolutely, and that it is one of the key kind of use cases for underground storage and the reason that it is being considered. So importantly, it will play a role alongside other storage technologies such as batteries. So as we continue our rollout of renewable energy technologies and increase that mix in the grid, we increasingly need to consider the effect of periods with low or no renewables. That is when the sun stops shining or the wind stops blowing. For shorter periods, batteries do an excellent job of filling this gap. They're a proven technology working at scale now. However, for longer periods, such as days or weeks, this is where hydrogen can play a role. So how this works, in times of excess renewable energy, that excess is converted into the molecular form into hydrogen, stored underground in large quantities, and then we can tap into that in times of low renewable energy output, converting that back into electrical energy through the use of gas turbines or fuel cells. So in summary, yes, it certainly does have a role to play.
Great, thank you. And there's a second question here for Elodie and Terry, perhaps. So energy security and reliability is highly topical. Can I ask if we decided to progress hydrogen storage today, how long would it take us to have a functional system in place? Perhaps Elodie, do you want to start first, and then perhaps Terry, if you've got any additional comments?
Yeah. Okay. Thank you. Yeah, it really depends about the technology. We talked about salt cavern, porous media, line mine rock cavern, and about the country as well, because you have to take into consideration some permitting phase, and depending on the countries, it could be more or less longer. But have in mind that so it really depends about the size you are targeting as well. But let's say in between 6 and 8, 10 years. So depending on technology and the size you are targeting. The longest is probably the line mine rock cavern, because you have that phase during the construction phase about installing the liner. So that's clearly something additional, and depending on the size again, but take into consideration that you have to add 1-2 years during the construction phase just because of the presence of that liner.
Thank you. Terry, any other additional comments?
Yeah, for sure. So whilst I haven't been directly involved in the project developing underground hydrogen storage facility itself, I can speak to the other side of the equation, which is large-scale hydrogen production projects that would ultimately supply that storage facility. And this kind of links back to a point that I made earlier around project timelines. So for a large-scale hydrogen project, from the moment you say, all right, let's start investigating, let's do the design, through to first hydrogen production, you're typically looking at a period of around 7 to 8 years. So that timeline is driven by a couple of key things. One is the complexity and first-of-a-kind nature of these hydrogen projects, particularly at scale. And when we're looking at underground hydrogen storage, we're considering gigawatt scale electrolysis to support. There's multiple layers of approvals and regulatory processes as well to work through. And then again, challenges with procurement lead times, which, as I alluded to before, are improving, however. So then, yeah, layering underground hydrogen storage on top of the complexity of a hydrogen facility, it's probably pushing to that 8 to 10 year timeline for sure.
Thank you. It's important we get it right. But thank you for your answers today. We have another question, and this one's for Andrew Feitz. Why the focus for onshore depleted gas sites? Is there a plan to look at offshore as a potential option into the future? Andrew.
All right. Well, thank you very much for the question. The issue there is that it is, my understanding is, currently illegal to store hydrogen offshore, and that's because it's not covered under, it's not permitted under the London Protocol on sea dumping. So we would need, like CO2 storage, we would need potentially an amendment to that protocol to enable offshore storage. That's the same whether it's salt storage or depleted storage in a depleted field. So that's the key reason there. Also, the costs will be potentially higher offshore. That's not to say that there's other countries not looking at offshore storage. I think there's a lot of potential. I know Canada and Ireland, for example, are very keen looking at offshore storage in salt. But I think there's some international agreements that needs to be sorted out. I see Elodie's looking very interested. Elodie, did you want to comment on that?
No, but clearly we prefer to go onshore for a question of cost, of course. But there's an option offshore as well, as you said. But yeah, definitely the onshore option is the easiest one.
Right. Okay, thank you. Another question here. Maybe we can start with Elodie, but anyone can jump in as well. What are the implications for water use in the different techniques, considering the cost of desalination and the environmental implications for saline contaminated water outflows? Elodie, do you want to start with that?
Yeah, no. So water use, you said.
What are the implications for water use in the different techniques? So, how much water do you need to use, and also what are the implications for perhaps the wastewater that's generated as a result, perhaps of dissolving salt caverns underground using water?
Yeah. So again, that is very dependent on the countries and on the location of the asset. If you can use depending on the location of the project, but you can use seawater. There's no issue about using the seawater. The only thing is that of course it is salty, but the brine at the exit will be 10 times more. The content of salt will be 10 times superior to the seawater. So that's not the process of leaching will be a bit slow, but that's not at the scale of the project, not visible really. You can reject the seawater, that brine into the sea as well. You need a permit to do that, and you do it properly on a certain way, but that's something you can do. And if not, usually we use raw water. There's more than 2,000 salt caverns in operation worldwide. We've been involved in many of those projects. We have never seen any issue regarding the use of the water. That's probably because we have aquifer that we could use, raw water available. So in Australia, it could be a little bit different, because if you are in the middle of the country, you need to find a source of water, and that could be sometimes difficult. Sometimes you have to build kilometers of pipeline just to transport the water. So that's additional cost to the project. So that's difficult to answer, because it's really on a case-by-case basis, depending on the location of your country, but of your project. But yeah, maybe Andrew, you want to add some.
And maybe to add something that when the economics is there, we also are working with companies in the United States and in Mexico. So what they do is that they inject water, brackish, fresh water, depending on the case. When they retrieve the brine, it's a highly valuable product. So sometimes you don't have any industry close by, so it's not economical to build a plant just for this. But some companies try to really have the synergy of using this brine, like valorize this brine for like some industry, like and building like for example, like all the salt that is used like for icy roads and things like this. So there's a lot of things that can be done with this brine that can be valorized if the infrastructure is there.
Yeah, that's a very good point, Capucine. I forgot to mention that. And what's important to take into consideration in that case as well, sometimes the salt company exploiting the salt, don't realize that they could capitalize on that project on both sides. Exploration of the salt, and as well storing, using those caverns after that to store energy. Sometimes they do not design the cavern properly for storage, but yes, it's good to think about it from the beginning to have that to added value.
Yeah, the whole life cycle approach to the project. So
yeah.
Now we do have another question for Terry. It says here, line pack works well for natural gas and is regularly used. For hydrogen, I understand as pipeliners are concerned, the extent of pressure cycling, if a hydrogen pipeline is used for line pack, it creates fatigue and reduces the life of the pipeline. What are your thoughts on this?
Yep, okay. So I think to start, I'm going to talk about a phenomenon known as hydrogen embrittlement. So this is kind of one of the core challenges with handling a hydrogen molecule compared to methane or natural gas molecule, and it comes down to the size. So when we transport hydrogen in a pipeline at pressure this phenomenon known as hydrogen embrittlement is where the molecule can actually work its way into kind of tiny little fractures in the steel. And the comment is correct that cycling the pressure kind of exacerbates the issue. That being said, if during the design phase, we know that there is going to be this constant cycling, that the pipeline can be designed accordingly to accommodate rapid changes and constant changes in pressure. So yeah, absolutely, it is a challenge, and it will result in a more expensive pipeline. But yeah, not a showstopper.
And
Great.
in Europe, they have designed, sorry, Douglas, if I may add, they have designed the backbone and they plan to build storages in between to limit the fluctuation, the pressure of that pressure, and to keep the pressure quite high during all the alongside the pipe actually.
Yeah, great. Thank you. Okay, so another question. I might throw to Andrew as the geologist first, but we'll see where we end up.
Can I just declare I'm an environmental engineer, but that's okay.
Okay, all right. You're masquerading as a geologist, that's okay.
Yep.
All right, so related to underground storage and other mixed gases, methane was mentioned. Has there been any assessment of Australian-based sites and mixing of radon and progeny? For example, in the unlined granite rock cavern model example, are there any risks of concentration of naturally occurring radioactive material or norms in the process? And is there a risk of worker exposure during the maintenance activities?
Well, that is a very good question, and I can honestly say I don't know. But look, I think one of the aspects is that the risk would be diminished if you're using a lined cavern. However, look, I will pass over to perhaps Elodie or Capucine for some comments on that with their experience.
Capucine, you want to take it first? Or?
Yeah, that's a very interesting question. So for example, we have the example of unlined hard rock cavern, and they're used for storing hydrocarbons. And there are strict rules on there is some analysis of the product that enters the cavern, and there is some analysis of the product that exits the cavern, and that's things that are critical to ensure that whichever company is using the storage is getting the quality product that they need. And I do not recall any case where this came up as an issue, but that's definitely an interesting point to keep in mind for any future design. That's a very important, interesting point. Yeah.
Yeah, and I presume as part of the regulatory process, those sorts of things would be considered, and you'd have to make a due diligence process around that aspect of the project.
Correct. Yeah.
And we have studied some because the question when the hydrogen started was, can we mix the hydrogen with the methane, with the natural gas in the storage, and the result was we talked about 5%, 10%, 15 up to 15%, but at the end the conclusion was not to do it for an economical point of view, because the value of the hydrogen is much higher than the natural gas, and at the end is all mixed, and there's no really economic interest of doing that. Regarding contamination, we have done some studies in porous media with the high storage project, so you can find out quite a lot regarding microbiological activity in this type of underground storage.
Yeah, great. Thank you. Perhaps slightly related too is another question, which is, given it's not as demanding to confine, is ammonia still discounted as a possible medium for hydrogen storage? Who'd like to take that one?
It's certainly not discounted. Yeah.
Short and sweet. That's good.
Yeah. No, there's examples of it around the world at the moment. But look, again, I'll refer to my geostock colleagues who have a lot more experience in this. Yeah.
Well, regarding ammonia, we don't see as many projects as hydrogen. just because the process involved is quite, I mean, you need to produce the hydrogen first, then to produce the ammonia. So it's very good carrier from an export point of view, so to transport it by sea. But then once you arrived, you need to crack the ammonia again. The transportation of the ammonia is not very easy, not very safe. So the pipeline has to be very short. And then you have to you use, so the process chain is quite long compared to the hydrogen. But yes, we know that the ammonia is used as a carrier, is used as well as a fuel, bunker fuel. So it's very difficult to give an answer because you see, that's really an important question, because when you are in an industrial cluster close to the sea, you don't know what to develop. Do I develop a tank for ammonia, underground storage for ammonia, or do I develop storages for hydrogen? So the question is quite difficult. So, but the price is not there today. Yeah. More questions.
So go ahead there.
Yeah, I'd just like to add a point on that. And it comes down to those industries that we refer to as hard-to-abate sectors, and which ammonia absolutely is one of those. And so yes, can be used to store hydrogen, and then but we do have the energy efficiency losses as we convert, as Elodie said, to ammonia and then back into hydrogen. Where it really shines is where we just use that ammonia directly. That kind of where it has the most benefit. So predominantly in fertilizer production. So yeah, just wanted to make that clear that is a kind of one of the greater use cases for ammonia.
And just to give an example, in the United States, there's one unlined mine cavern which has been used for ammonia for like several decades, and it recently got converted to another product for storage, but it's something that has been done technically.
I was going to add there, with the use cases, one of the major use cases of ammonia, direct use of ammonia, is in shipping. So that's one of the low carbon fuels that's being seriously considered for shipping, along with methanol. So yeah, if you don't have to crack it when it gets to the other end and you can use it directly, then that could be a really effective use of hydrogen derivatives.
Great, thank you. Probably just related to this is a question about what sort of industries would be required to have such large amounts of hydrogen storage. And you touched on it a little bit, but I wonder if you could expand on that a little bit too. Who would like to start?
I'll start with some work that we've looked at for green iron and green steel, actually. If you're looking at if you want to establish a plant in an area that doesn't currently is not supported by transmission lines, but has excellent renewable resources, got good water resources, good access to iron ore, then you could look at an islanded system that's not connected to transmission lines, because it's really expensive to put in transmission lines. I believe it's in the order of $1 million per kilometre to put those in. So it costs quite a lot. So if you can build a plant with sufficient hydrogen storage in combination with battery storage, you could run potentially that plant completely using renewable energies, but you do need that backup of the hydrogen storage there. So that is one use case that we've been working with Monash University, looking at different ideas of how you could get off the grid for some of these really major projects.
Yeah. Any other industries you'd like to add?
What you said, and very clearly in Ireland, one of the biggest projects we have in line mine rock cavern is that one, and the off-takers are data center. So that will be clearly in part of their scope too, to use green electricity. So they want 100% of green electricity, and they have quite a lot of renewables, wind energy. But of course, you have to cover that time where the wind is not blowing, and that's why they are looking for massive quantities of hydrogen to put it back in gas turbine to the grid and produce electricity again. So one of the big clients for Hydrogen could be data center to produce green electricity, but also heavy industries, as you mentioned, the steel factories and refineries as well could have that need. And maybe an additional one is about, we talk about a lot about producing sustainable aviation fuel, and you need hydrogen for that one. And the regulation is changing quite a lot, and at some point we will need to add more than 30% of SAF into the jet fuel. So that's something we see coming as well.
Great, thank you. Any other comments? No? Okay, all right. One more question. What will be involved in the decommissioning and restoration of various types of underground hydrogen storage facilities at the end of the project? Who wants to start with that one?
The decommissioning of the
and restoration,
okay.
So these are things that are, and I believe it was also part of the studies that Geostock performed for Geoscience Australia. And it's very typical that when you plan for an underground storage, you plan for the decommissioning. And most of the time it's driven by the regulators. Like when you plan for like drilling a well, you have to plan for like the plug and abandonment of the well. So the same with the decommissioning of this cavern. Like it's a slow process. I mean, it's like it's a long process. It requires some monitoring after like the abandonment of the cavern, but it's something that is part of the design of the cavern, even at the early stage. It's really something that you cannot avoid when you are creating the cavern. You already have to include it according to, and most of the time it's to abide by regulators.
And we have decommissioned already some cavern. But it's clearly because of an economical point of view, just because the cavern was not working enough and the cycle was not used enough. But to give you example, today we operate caverns that have 60, 50 years old. It's usually if you decommission an asset, this kind of asset, it's because the economics are not there. You put the storage on hold, but it's the probability of having to do that because of the technical aspect is quite low.
Okay, thank you. So probably our last question for today, and it's probably best answered by Andrew, which is how do you go about exploring, assessing and developing lined rock caverns in Australia?
Okay, well, you've worked with really talented organizations that have done this for decades for a start. No, that's seriously, it's been great working with both Geostock and Lane Power in the US because they do have a lot of experience and it gives you great insight into what are the practical considerations when you're looking at building these caverns or designing the caverns and looking at the suitable aspects of them. So, I mean, the key thing is finding the right sort of geology. That was a key finding, I think, out of both the studies, particularly the Geostock study. And once you've sort of identified, and in terms of the right geology, what you're essentially looking for is a surface expression or very near to the surface of a hard rock geological feature. So you don't want it too deep, because we don't want to build the cavern too deep. We want it to look in the order of sort of 100 or 150 meters, but you want that sort of a good whack of the solid geology above your cavern. So in a way that really helps narrow down what you're looking for, because you're looking for these sort of surface geology expressions or areas where the rock is not too weathered on top. And then there's a very long process to prove up whether that geological feature is going to be suitable. So that requires would require seismic surveys over that to look at the profile and the nature of the rock and the structures and stuff. drilling wells to test the rock and collect samples. Yeah, there's a very, very long process of proving up whether or not that geological feature is going to be suitable before you even think about really, building a cavern in there. So it's quite an extensive process. I'm not sure if my Geostock colleagues want to comment further on that.
No, just what we mentioned as well is depending on the country, the permitting and so on. But yes, take into consideration that you need few years to develop that. In between 1 and 3 years to carry out all the phases, the studies, let's say, and the site investigation mentioned by Andrew. And then for the construction phase, you, depending on the size you are targeting, but add 4 years, additional years, or maybe more, if it is line mine work cavern. So
Great.
a long
Thank you.
process.
Yes.
So you have to start now to be ready by 2035.
A call to action, I hear. Yeah, great. Well done. Well, look, thank you, Terry, Andrew, Capucine, and Elodie. It's been fantastic to have you all with us today. And thank you, everyone, for some great questions there. And if we couldn't get to your question and you have provided your name, we will respond to you directly in the next week or two. And you can also email us. I'll share the address shortly. But as you've heard, this work is more important than ever as we face today's challenges and embrace the opportunities posed by the energy transition. Global geopolitical events and, importantly, maintaining Australia's position as a competitive global investment destination are key to underpinning this work. So that brings us today to the end of the proceedings. Thank you again for joining us and sharing your thoughts and comments. We're planning more webinars this year on a range of topics. And so to hear about them early, please visit our website at ga.gov.au, or better yet, subscribe to the Resourcing Australia's Prosperity newsletter via the link. Future webinars will be improved by your feedback, and we'll be sending a link to a 5-minute survey, very short, for everyone who attended today, and we'd really, really appreciate it if you could fill it out and provide us your feedback on how you found the webinars and what we could do better. You can also just snap the QR code. The recording of today's event will be on YouTube in the coming days. And remember, you can also email any of the questions you have to rapinitiative@ga.gov.au. We look forward to hopefully seeing you at the next webinar, and thank you for joining us today.